part of. It's like 80% of it.
It's like doing another homework to me. And that's what I was frustrated about. It's like, I'm not going to keep studying and reading the book and reading other books and asking people questions when it's a waste of my time. Who knows how to do that?
Right, now I feel extreme pressure
To do well.
Okay, so how did the test go? I haven't had a chance to look at them yet. I'm gonna grade them this afternoon.
Really
so
well.
We should get back. Went okay?
Mm-hmm.
Nothing. Oh.
I think before I studied using like last year's homework and stuff, I think it would have been really, really hard because you have all these tools, but they're also theoretical and like you haven't used them yet. But once you had seen a couple of practice problems and everything was, I think, pretty standard.
Okay.
I derived that equation you said was going to be on the test. It took Monica and I an hour, and it wasn't on the test.
That was good for you.
Bill's character.
It was just a little bit of algebra, right? All right. What I want to do is, today I want to go over the use of imaging spectrometers and see how we get ground observable data based on this sensing technology. It's not new anymore. I mean, it's been around for 20 years now. It's funny, people still refer to it as, oh, that new hyperspectral stuff. Well, I mean, it's been, there's a lot of history to it at this point. It's very mature. The sensors are great. But the exploitation of the data is still a mystery to a lot of people. And a lot of folks just use it as it is, right? So imagine you fly a spectrometer and you collect radiance data. And you have radiance reaching the sensor. You have these very fine spectral signatures, right? I mean, you'll have curves as a function. All right. So you have curves as a function of wavelength. Let's say you're just measuring radiance. And you might have hundreds or even thousands of spectral points depending on your sensor. And I'm totally out of control. Let's use this. All right, so you'll have curves, right? You have lots of spectral structure in them. They'll look, but something like this is a function of wavelength, and that might go from 4/10. Sorry about that, John. Should be able to see it now. All right, so from 4/10 out to, let's say we're working in the visible portion of the spectrum, so out to 2.5, as we've always been saying. All right, and when somebody sees something like that, all of a sudden they think they have really good information, right? Well, why? Well, because they have lots of data points, there's lots of structure in there, and all of a sudden people start to trust this. Well, why do they start to trust this? Well, because it's coming from this new sensor that everybody's been saying has been a fantastic new innovation, costs all this kind of money, and all of a sudden they forget a little bit of the physics that's going on that hopefully is being ingrained into your head right now. When you see something like this, and maybe I drew it a little bit too smooth, but let me start to put some wiggles in here. All right, I'll stop. All right, you get the idea. If you start to see a curve that has some structure to it, like this, what's the first thing that pops into your head? What are you looking at? Noise, absorption. Right? When you plotted transmission in the Modtran lab, what did it look like? Was it a nice smooth curve, or did it have a lot of structure to it? A lot of structure. All right, I think if you looked at that, you saw a lot of little wiggles on there, and that's the absorption lines from the atmospheric gas. It could be noise, right? But typically they try to balance these sensors very well, so you don't see a lot of wavelength to wavelength changes. So if I had a constant radiant signal at the front end of my sensor, I should see a constant response out of these detectors because the individual detectors along the array that they're using are balanced fairly well so that you don't see any discontinuities because of radiance. There's a little bit of noise, but not a lot. Okay. All right. In 99% of the sensors, I'm not saying there's not a bad sensor out there, but 99%. So this is a lot of atmospheric, and the minute you start to see this kind of stuff, you have to realize, wow, you know, I shouldn't go ahead and just throw this into NV and try and do a land cover classification or something like that. And we'll talk about those things a little later in the quarter. But I have to do something. I have to fix this data before I use it. I have to remove the atmosphere. You know, just like we've been doing with single band and multiband sensors, with these hyperspectral sensors, we need to do the same thing. But the nice part is, with these sensors, is we have a lot more information. We have, like I said, hundreds or thousands of bands across the band paths that we're working with. And what that gives us is it gives us an observable that we really never had before. All right, it gives us a view of the intervening atmosphere. And so we can see the structure of it. And hopefully, knowing that structure, we can do something to remove it without as much need as we had in the past for ground truth or known objects on the ground or flying at different altitudes. Maybe with a single shot we should be able to do something. So that's what I want to go over today is a couple techniques on how to do that in the visible wavelength region. And I brought in a Fourier transform infrared spectrometer to show you just, so you can see one of the devices. But we'll go over a paper that does what's called temperature emissivity separation, right, from a sensor like this, working on the removal of the atmospheric effects that we see here, right? All right, so let me go back here for a sec. Just check one sec, make sure I can hear. John, is everything okay now? You can see and hear? It's not a good sign. Oh, okay, perfect. All right. So let's think about what we see. Once we get a signal at the front end of the sensor, we have a combination of the energy that's reflected from the target. We have the path radiance, the upwelling term. We have the skylight that's been reflected from the target up to the sensor. All that combined propagates back through the atmosphere, is affected by the transmission term, and we get a radiance at that front end of the sensor. All right, so we've been calling that L to this point. So this L that you see right here, with the subscript of delta lambda, now is exactly that same term, but the delta lambda indicates that it's in a very narrow wavelength band. Okay, so we're looking at a very narrow wavelength band, maybe 10 nanometers wide. The typical hyperspectral sensor in the Vernier-Sweers region of spectrum is 10 nanometers. Some are even narrower than that, but most of them are around 10. So much narrower than we've seen with any broadband, visible, or even multispectral systems to this point. All right, so that's the notation. All right, now, that's the radiance that's reaching our sensor. In the denominator here, what we have is the exoatmospheric solar radiance in that same narrow bandpass, reaching ground, and incident in a normal direction onto the target that we're looking at. Right, so the ground reaching radiance. Okay, so this term, we always know, right? We know the exoatmospheric solar radiance. So, as long as we know the time of the year, the distance from the sun, we can look that up in tables as a function of wavelength. Very well documented. And we know from the time of day and the day of the year, we know the elevation angle or declination angle of the sun at any particular time, so we know cos theta. Right? So we know this term all the time. We measure this term with our sensor. All right, so that's kind of unfortunate because those are two things we can do well. We put a sensor up, we can measure radiance, and we have tabulated values over the years of what the atmospheric solar radiance looks like. So if that's all I have, and we think about this for a second, this term, this ratio of what's reaching the sensor over what's coming in an incident onto the ground is a combination of what we've been calling the L-path transmission, the transmission from the sun down to the ground, back up to the sensor, right? So that's tau 1 times tau 2 in that same narrow wavelength band. And then that's modified by the reflectance of the target that we're looking at, right? So if we know the radiance reaching the target, we know the radiance down onto the target, or at the edge of the atmosphere, propagating down towards the target. If we know that ratio, that ratio is sort of this, right? I mean, it's the radiance at the edge of the atmosphere times tau 1, reflected off the target, back up to the sensor through tau 2, and that's L. Right? Now, why is the approximately equal there? What's missing? Yeah, the upwell and the downwell term. All right, so those are missing. So this is approximately what we're going to look at. All right, now, the nice thing about the upwell and the downwell term in general is that over a scene, it's constant. All right, for a majority of a scene, you'll have a constant upwell and downwell radiance. So if those are just a multiplicative constant and an additive constant, this ratio will still tend to be constant. Right? So it's a multiplicative constant. That ratio will tend to be constant. The additive term has a little bit of effect. Right? So we'll get a little bit of an error. But what I want to do here is I want to try to avoid all that at this point and use just the two terms that we really know well and see what we can do with that. And see how we can get to a calibration. All right, so let's call the ratio of the radiance reaching the sensor to the exoatmospheric solar radiance R, right, for a particular wavelength. Okay. Now, when you look at some radiance data, this is radiance data as a function of wavelength. This could be very indicative of what you might see from a hyperspectral, a really, really fine resolution hyperspectral sensor. This is just actually a radiance curve out of Montran. You see all this structure. All right, so now let's take this to a fairly moderate resolution and spectral resolution, hyperspectral sensor. All right, so let's imagine that we have a hyperspectral sensor, and these are sensor response functions for 3 adjacent detectors. Okay, so one is about 50 nanometers wide. This one, another 50 nanometers wide if you go full width at half max, and the same thing here. So 3 adjacent 50 nanometer wide sensors. So this is a fairly coarse resolution. So you imagine you would integrate the signal from about right here to about right here, modified by this Gaussian shaped spectral response function. You do the same in this region, right here, and you would do the same in this region over here. Right? So over here you get a point, probably integrated, came to about where my pointer is. This one, maybe get a point about right there. And then over here, you probably get a point, it's about like that. Imagine do those integrals and you come out with those values. All right, and you did that for one of the Landsat bands in the lab you just finished up. All right, so if we do that, we'll get a fairly coarse spectral shape that represents this very fine spectral shape that we see right here. All right, so what can we do with something like that? All right, well, you got to understand a little bit of the physics that's going on. If you think about the sun, it's a 6,000 degree, burning gas star. I don't know what else to call it, but it's essentially a black body. Right? If you were in space looking at the sun with a spectrometer, and you looked at the radiance curve, and there was no intervening atmosphere, it would look very much like a 6,000 K black body. Okay? But when we're on the Earth's surface, it doesn't. Right? And that's because the absorption lines in the atmosphere, all the gases that exist in the atmosphere, modify that black body signal before it reaches the ground. All right, so this particular dip in the spectra right here could be due to a couple things. It could be due to the reflectance of the target that we're looking at on the ground. It might be that at 940 nanometers or so, it has a lower reflection than it does out of 1,000 nanometers. That's one explanation for a curve like this that you would observe at the sensor. The other explanation, and probably, I don't want to say the right one, but probably the better one, is that the atmosphere tends to absorb a lot of energy, right at 940 nanometers, because there's a water vapor absorption line right there. Okay? The water vapor in the atmosphere tends to absorb a lot of energy at that wavelength, so we don't get a lot of energy to the ground. So even if you had a perfectly white target that was, had 100% reflectance across the entire spectrum, you would still see this dip. Okay? You'd see that if you looked at the transmission curves that you did in your lab, you should see a dip right around 940. Okay, so we always know we're going to see that dip there. All right, now, what do you think, if you go outside and look, from RIT and you look towards downtown, for instance, there's days you can see downtown and very clearly, and there's days you can't see downtown very clearly. What do you think is the prime culprit that makes it less clear on some days than others? Water vapor. Right? I mean, it's those hot, humid days, warm, humid days that you might get in Rochester, right? Where you go outside and you look downtown and it's hazy. And then most of the days it's very dry and very clear when it's not raining, right? So it's the water vapor that is the prime culprit, at least in our visual wavelength region. It tends to be true across the entire visible wavelength spectrum also. The water has a lot of absorption lines, very large molecules, they scatter a lot, so they really affect visibility. Other things that affect visibility are aerosol particles. So if you grew up somewhere near a farm, you know there was those days when it was a little bit windy and some of the particulates of the soil got suspended in the atmosphere, right? Those small soil particles will tend to make it very hazy. If you grew up near the ocean, there was those days where you had a very maritime, soupy atmosphere where a lot of water vapor came up off the ocean, a lot of salt particles maybe came up, and you would have scattering that occurred because of those also, right? So aerosols play a big effect too, but water vapor is a big culprit. So one of the things that we can do when we try to characterize the atmosphere is to use a model like Montran, right? We can use something like Montran and get a really good description of what the atmosphere looks like if and only if we have a really good estimate of the inputs, right? If you know the atmospheric parameters to put into Montran exactly, you're going to get a very good representation of what the atmospheric transmission, path radiance, all the terms look like, right? But the key is trying to get those input parameters. And that's what I want to try and show you how to do from hyperspectral data. How can you start to arrive at those? All right, so like I said, one of the big ones in the visible wavelength region is water vapor. So we're going to look at a technique right now to get water vapor. All right, so imagine this. If I integrated this curve, these three spectral response functions, I get 3 points. Okay? If I took a look at this point from the band to the left of the water vapor absorption line, and this point over here, the one to the right of the water absorption line, and I thought about what the sun should look like, I should just connect those 2 points. Right? It would kind of just be a smooth black body curve between those 2 points. So you probably see something along the lines, if I was able to draw in here, follow my cursor for a sec. If I could just draw a nice smooth line across here, that would probably be very close to what we would see on a Planck curve at 6,000 K. Right? But because of the water, we get this dip. All right, so imagine if we did this. What if I took this point right here, and I literally just drew a straight line to this point over here. So just a linear interpolation between those 2 points. And then I said, all right, at 940, I should have a point that falls right where that cursor is, right on that straight line. But I don't. I have one that's down. Okay. So if I could go ahead and compute the ratio between what I would expect to get, that interpolated value, and what I do get, the actual integrated value down at this point, right? I've come up with a value, a ratio between those 2 points, and that ratio would represent how wrong I am or how right I am from my black body assumption. So what could I do in Montran to make that ratio change? I could definitely change the aerosols, but remember where we are, right? We're at 940 right now, so we're in the water absorption band. So I can change the water vapor input, right? I can go into one of the standard atmospheres, or I can go into a radiosonde, and I can change the column water vapor. Right? It's one of the parameters that you can change in Modtran. All right, so if I went ahead and I took my observed values, right, and I had a value here, and I interpolated between them, and I had a measured value here. So imagine that this is actually a measured value right here from my sensor. And I took the ratio between my interpolated point at 940 and my observed point at 940 from my actual data, from my spectrometer data. Okay, I'd get a number. Now I run Modtran, and I make my best guess at what the atmosphere is. Right? Then I look at this point, I interpolate between them from the Modtran data, and I look at this point right here, and I compute the ratio. And it's too high in my Modtran, right? That means that this absorption line is too shallow. Okay? If the ratio is too high, it means this absorption line is too shallow. So what do I need to do? I need to deepen that absorption line. In order to deepen the water absorption line, what do? Put more water in the atmosphere. So I increase my water concentration. And I run Modtran. And it gets a little deeper, but the ratio is still too high. So I run Modtran again. Until I keep running Modtran over and over again, until I get that ratio to be identical to what I observed in my sensor data. The only way to do that, the only way to make that happen, to get those ratios to be the same, is for me to be actually getting closer to the physics that's causing it. So if you believe Modtran is doing the physics right, and we have to have faith that that's the case, right? They've been doing it for a long time. Once you can get that simulated data to match your observed data, then all of a sudden you have a good handle on what's going on physically in your scene. So now I know the water vapor concentration. If I then run Modtran with that water vapor concentration and my best guess at aerosols, right, for that particular scene, I should then get what? Well, what did you get out of Modtran? Well, you got out a transmission curve. You got out an upwell radiance curve. You got out downwell radiance. You got out all the terms that you then need to go and invert your radiance down to reflectance on the ground. Does that make sense?
So is that only going to match up for this particular water column or water absorption band? Or is that going to match up for every single one?
Well, it's gonna be really good right here. Okay. Now there's other water absorption bands. So what you could do is you could do the same sort of a matching technique in all the water absorption bands. Right? And this is a very basic technique on how to do it. There's folks who have done it, exactly what you just said. Take all the water absorption bands in between 0.4 and 2.5 microns and look at their ratios at all the locations. And now, when you go through your optimization by running Modtran multiple times, changing the water vapor concentration, when do you stop? Well, you stop when the ratio in all of the bands, in a least square sense, is closest. Exactly.
So when you talk about ratio, it's the ratio between what you get in Modtran for that specific absorption line and what you observe.
Yes.
Okay.
Yeah. So. So let's say we have L at the sensor, right, as a functional wavelength. And there, you're going to get a point here, a point there, and let's say a point over here, where this is really hard to do without anything else. Okay, 940 nanometers. All right. Now, in Modtran, call that L, that's an M, okay? You'll get a curve that looks like the one we've been looking at. All right, so You observe this one, you observe this one, you observe this one. Draw a straight line between those two, interpolate to that point, and compute the radiance ratio between those 2 points. Montran, as you run it and change the water vapor, you'll get a curve that looks like this. If you get less water vapor in there, the curve will come up a little bit. Less water vapor, come up a little bit more. No water vapor, right? You get a black body curve. Right? So you could, again, take this point right here, interpolate between them, and compute the ratio here, the ratio there, and the ratio there. And once you get a matching ratio between these two, so probably this curve right here, that's how you calculate water vapor, at least that one wavelength region. If everything is working well, the same thing will hold true in other water absorption lines throughout the spectrum. That's not sitting well with you.
But the points over there were integrals of a much wider
These points.
bands. Yeah.
These points. Yeah, absolutely. I'm sorry. You need to go ahead and integrate Montran here, here, and here by the same spectral response function as you did over here. Right. So you need to know the spectral response function is centered to integrate your integrate your Montran equivalent spectral bands. Right. So when I said draw a line from here to here, this is an interpolated point. I'm sorry, an integrated point. This is an integrated point, and this is an integrated point based on yes, the spectral response curves that you need for that sensor.
So you use the response from Montran, the response curves for each band, then you integrate, and then you interpolate and you fit ratios.
Yes. Does that make sense, everybody? All right, well, that's kind of neat. I mean, there's no other data set that we've had to this point where we've had enough data as a function of wavelength to be able to do something like that. Okay, now, does that solution hold for every point in your scene? I'm looking at Emery. Is the water vapor the same everywhere? No. Right? I mean, you could walk 100 meters one way or another in a scene, and if you were able to take a little cylinder and shove it up to space and get really, I don't know what I'm saying here, get really cold in there and absorb all that water and gather it all up, you would get the amount of water that was in a column above you. Right? And if you knew how much water was in a column above you, then you know how much water vapor is in that particular column. If you did that all over your scene, you'd get different levels of water that you got out. And that's because water vapor is very highly variable over, even a moderately sized scene. If you went from here to the Lake Ontario shoreline, you would have a great deal of modification in your water vapor profiles. Okay. So, what does that imply that you need to do? For every pixel. Right? So, if I have this data, right, at every pixel in a hyperspectral sensor, I have a full spectrum. I have these 3 points for every pixel. I could do this solution and figure out the water vapor concentration at that pixel. Then I can move 1 pixel to the right and do it again. Move 1 pixel to the right, do it again. I can do it for every single pixel in the scene. And so now you can go ahead and you can atmospherically correct every single pixel in your scene independently using a different set of parameters that you got out of Montran for transmission, path gradients, and downwell gradients. Okay. And as a byproduct, you could even produce a water vapor density map over your scene. And so that's a lot of information for having to do very little real work when I say real work, I mean you're not collecting any ground truth on the ground. You're not doing anything besides looking at the data that you collected with your sensor. Now, where does real work come in? Every pixel. I don't know how many Modtran runs you want to do here. But let's say you do 100 Modtran runs, right? So you have really fine resolution, and you have 1 million pixels in your scene. Now you're going to be really happy you know how to use that research computing cluster, right? Because that's where these kind of things come into play. That's a lot of long runs. But infinitely possible.
How much would it hurt you to not calculate every pixel and do interpolation much like a Bayer filter would?
Yeah, absolutely.
Gaps, right?
Absolutely. Do you think it changes? Let's say you have a one meter pixel on the ground. Do you think it changes every 1 meter? Probably not. Well, the answer is yes. It changes probably every meter. Does it change significantly every meter? Probably not. Can I go every 10 meters and interpolate? Sure. And that's how you cut down your runtime. Yeah, absolutely. I wouldn't go too far
Right.
with water vapor, but you play around with it, you get a feel. If you're doing this in a desert, you can go every 100 meters, every 200 meters, who knows? And so it really depends on the area that you're in. Okay. So, I think that's shown here, right, in the next couple slides, right? Here's the 3 radiance values, the interpolated value, so you can follow through with that. All right, now, another method that you can approach this with is very similar, right? And it's called inversion reflectance using nonlinear least squared spectrofit. Just a fancy name for exactly the same thing that we just did. All right, now, the assumption here is that the reflectance at any wavelength is some linear function of the wavelength itself over some narrow region. Okay, so think about that for a second. The reflectance is a function, a linear function of the wavelength. So as the wavelength gets longer, the reflectance gets lower. Or as the wavelength gets longer, the reflectance gets higher. It's some just linear function with an offset curve. And then on the slope. All right. If you think about that, and if you look at reflectance spectra, you look at enough reflectance spectra out there, let's just try something right here. Reflectance of, pick a material.
Concrete.
That's the first one. Let's see. All right. All right, reflectance of concrete.
It's not linear.
Well, it's not linear. But if you pick 2 points, or 3 points, or 4 points, or 5 points close to one another, 50, let's say 10 nanometer data spectrally, and we look at, 5, I don't even know what this is a plot of. That's not a reflectance
temperature
here.
profile.
Yeah, that's not. All right, so.
You could try Google Images and stuff.
All right, there we go. Spectral reflections of different granules. All right, so pick any 5 adjacent points at 10 nanometer centers. All right, so let's see. Here's 540, here's 600. So each tick mark here is 60 nanometers apart. If I went from here to here, linear? Sure. Here to here, linear? Yeah, here to here, linear? Yeah, pretty much. Here to here, linear? Sure. Here to here? Most natural surfaces tend to be fairly linear over narrow wavelength regions, right? So it's not an unreasonable assumption to make. It's not perfect, right? But it's not unreasonable. All right. So let's say that's true. All right. Now, what we're going to do in this case is this particular technique takes 5 consecutive spectral bands, right, centered around 760 nanometers. All right, so this is a different wavelength region. This is actually an oxygen absorption that exists here. Now, the radiance that you can predict, right, from a propagation of all the energy using this reflectance curve. Right, so you get this. L sub hat is the radiance that you're going to predict using this reflectance curve and the exoatmospheric solar radiance, the downwelling radiance, the path radiance, and all of that, right, is L hat. Okay. Now that's going to be, what we're going to do is say that's some function, some nonlinear least square spectral fit function of the coefficients, A and B, and H naught. What was H naught? Go back to the beginning of class. That was the height of the ground, right? Or wait. No, height of our sensor above the ground. So it's the atmospheric path between the sensor and the ground in any particular location. So why does that come into play? Well, the more atmosphere there is, the more attenuation, more path radius, the more effect the atmosphere is going to have. All right, so what we're going to try and do is for a couple different reflectance values in your scene that we're going to assume are linear as a function of wavelength over some narrow bandpass region. In this particular technique, they use 5 consecutive bands, centered at this oxygen absorption line. We're going to go ahead and we're going to predict or compute the radiance values, and then we're going to fit a function, a nonlinear function, to the coefficients and the height, and come up with the radiance. All right. Well, we observe radiance, and that's what we get at our sensor. We can predict radiance, and what we're going to try and do is get a small error between our predictions and our observed radiances. And once we beat down this error enough, so it's as close to 0 as we can possibly get, well then what are we going to have? Well, we're going to have a function finally that fits well to our observed data. Well, what's that a function of? Well, it's a function of these two terms, right, which are just these kind of strange coefficients on a lambda to make reflectance a linear function of wavelength. So they don't really have a good physical meaning. But this one right here, that's a good physical parameter. Right? What would we, if we got a good fit and we knew H naught at every location, what would we have just produced? What's that?
Radiance for that variable. So if you know H naught and you know the approximation for L sub I.
Well, we come up with the approximation at L sub I, and we adjust these parameters enough so that it becomes a good one. But what have we been adjusting in order to do that? Well, we've been adjusting these 3 terms, 2 of which don't really have a good physical meaning to them. One really does. If I know how high my sensor is, and I know H naught now at every pixel, what can I produce? I can produce a topographic map. Right? So,
Couldn't you do that already? I don't understand.
how would I be able to do that?
You know your height of your sensor at every point, don't you?
I do.
So you didn't need to do this to know your height of your sensor at every point.
But you know,
I know.
the sensor in the atmosphere with respect to the sea level. Let's say, on your scene, you can calculate the height at each point compared to the sensor.
Yeah, so I know how high I'm flying above sea level. I'm flying at 1,000 feet. But now I know how far it is from my sensor to the ground at every point in my scene. Right? So that's not always 1,000 feet. Right? The variations.
Is that assuming your sensor is nadir all the time?
Yep. Yep, looking straight down.
You know what I mean though? Like the distance between the center pixel and the corner pixels.
Right. So if you're looking straight down, you'll get that point. If you're looking off to an angle, you'll have a different path term. Right? You'll have a different length to the ground, but you know the angles that you're looking at. You know the difference in that. As long as you can get the XY position correct, then you get right for that location. So what do you have here? Well, you have another, fallout, essentially. You'll get from this data that you weren't even expecting, right? You got a water vapor map from the last technique. Here you're getting a topographic map, essentially from your data, right? So just with a single sensor again, now we could do this if we flew and took multiple frames, right? We could do 3D geometric reconstruction of the ground, right? But this is just a single frame, a single hyperspectral frame that we come up with data. All right. So one of the things that you can do, or that you need to do here, though, is come up with all those parameters for those reflectance curves, those A's and B's. All right, so how do you do that? Well, let's take a look at this is kind of a confusing slide, but I'll try to walk you through this. Hopefully this will all make sense. So remember we said we had 5 spectral bands centered at 760 on this oxygen absorption point. All right, so here's the integrated radiance values at those 5 points. The lighter curve here, and they're right on top of each other, or real close on top of each other, but the lighter one is the one you observed with the sensor. The darker one is the one you predicted using the atmospheric model. Okay? So what I'm trying to show here on this particular illustration is that, by the time you get a best fit, they're very close to being right on top of one another. And they're not perfect, but they're very, very close. All right, what did we need to do? We needed to get a bunch of different reflectance values where reflectance was as a function of wavelength was a linear function of wavelength, right? That are this term right here. Okay. So if we took 2 surfaces on the ground, 2 arbitrary surfaces, that in this wavelength read. Oh, okay. I'm sorry. So 2 arbitrary surfaces on the ground. I saw a different wavelength region here. Right? We're back to the original wavelength region around the water absorption line over here. Okay? So you can go ahead and you can adjust the water vapor just like we did last time in the Montran model, modify your atmosphere, get your new L. And with several different surfaces, right, in this case we're just showing 2, A and B, we should be able to come up with our coefficients for this equation, where reflectance is a function of wavelength. Right? We have 2 unknowns, A and B. We need at least 2 different reflectance values, so we use 2 different reflectance curves to do that. 2 different surfaces. Come up with those A's and B's. And so now we have the A's and B's that we drove from our trick that we just used in the last technique that we were working with, where we're looking at the ratio of the radiances around the water absorption at 960. Okay. Now, what do we do? Well, let me go ahead one side here. And we're going to add another term to the equation. This is the equation that we were working with. What we're going to do is we're going to add a 3rd term, and this is what makes it the nonlinear version that we're using right here. And what is this term going to be? Well, this coefficient is going to look at the reflectance of water vapor at that particular wavelength. Right? So reflectance is going to be some function of the wavelength, a linear function of wavelength, plus some modifying factor that's based on the amount of water vapor in the atmosphere. Okay? So what happens? We put more water vapor in the atmosphere, the contrast of the scene drops, the apparent reflectance of a target tends to go up. It looks a little bit brighter, right? That little bit brighter is this additive term. It's just another offset that we're adding on. Okay. All right, so that helps us here because we already know a technique where we can go ahead and using the water absorption line, run Montran multiple times and get the water vapor correct. Right? If we can get that water vapor correct, then over here at around this oxygen absorption line, we can get a good fit at that location. All right, now, one other thing that you might want to do, so to illustrate that a little bit clearer here, there's two more plots. So here's leaf water absorption. This is just water absorption. I don't know where leaf comes from here. It's just the water absorption line at 960. Run that multiple times, get your best fit on your radiance value. Now, The other thing you might want to do, right, we've just been working with water vapor to this point, and because of that, we're kind of using one parameter to try and drive everything. But you told me there was other things that affected how much energy got through the atmosphere. And one of the things you said was aerosols, right? Particulates and everything. All right, so if we could go ahead and modify, using a similar sort of technique now, modify the amount of aerosols that are in the atmosphere, well then we should get a better fit. Right? So now, rather than just dialing one knob to get our atmosphere right, let's dial water vapor, get that as close as we can. Then let's dial aerosols, get that as close as we can. And between those two parameters, let's keep tweaking those. Right? That's a lot of runs to do, a lot of permutations of parameters to run. But eventually we get the best answer we can to our observed data. Right? So in order to do the aerosols, right, what we're going to do is we're going to look over vegetation. Right? Why might we look over vegetation if what we want to do is try and characterize aerosols in the atmosphere? Remember where we're looking again. We're looking out, you know, in the 700, no, beyond 700, so out around vegetation curve. Which one's the curve? This one's the vegetation curve, F. Okay, so here's vegetation curve, peaks at around 600 nanometers, so it looks green. All right, but what is not clear here is what wavelength region are we looking at? All right. What happens to vegetation? And I don't know if this is intuitive to you at this point yet, but as our wavelength region starts to grow a little bit past the visible wavelength region, where the vegetation looks green, what happens to a vegetation curve? The reflectance spikes.
It increases.
Yeah, it spikes way up, right? And around 1 micron or so, it's at its highest point of reflectance. Okay? So we have a lot of reflectance, a lot of energy being reflected off the target on the ground at that point above vegetation areas. So when you have a lot of energy being reflected off your target, now propagating through your atmosphere, does scattering start to have a greater or smaller effect?
Greater.
It was a 50%.
It was 50 cents.
Yeah.
50-50 shot.
You have multiple scatterings, so it seems like you're getting even more scattering.
Exactly. Because you have multiple scattering, you tend to have more energy being scattered around. You know, put more photons in, more get scattered around, more come back into the path. It tends to have a little bit more of an effect. So if we go ahead and we look in those absorption lines, those water absorption lines, right, we have a lot of absorption of the atmosphere. So we know we don't have a lot of photons to the ground. But if we look in that place and we get a lot of photons to the sensor, well then we know it's due to scattering and it's due to aerosols. Okay? So because we get this artificial increase where we shouldn't have a lot of photons to begin with, it's a good place to be looking to try and use that as a parameter to tune the atmosphere. All right, so we go in, and Montreal doesn't have a lot of control over aerosols. I mean, you could put in, I think there's choices like maritime, rural, urban, you know, very broad classes of aerosols. And those profiles are pretty good. And you really need to know the situation that you're in and make a good guess. Am I near a shoreline? Do I have an onshore breeze, an offshore breeze? You know, you have to make some good guess of what the aerosols are. But then you can change your concentration very easily, and that's done with the visibility term in Montreal. There's a term in the card deck called VIS. It's just how far can I see on the ground? And you say how many kilometers? 23 kilometers is one of the standard ones they have, but if it's 1 kilometer, 10 kilometers, you put that number in, and it'll adjust the number of particles, the aerosol particles in the atmosphere for that particular simulation. So you can go ahead and you can tweak that above vegetation, and again, generate more data that you can derive these coefficients from, right, A and B. All right, now once you're all done and you got good A and B estimate, because you've been adjusting water vapor concentration, you've been adjusting aerosol concentration, you get the best fit, and it's not going to tend to be a linear fit any longer. This will be a non-linear term here But we're still going to treat it as a linear equation and just come up with those values. So you can imagine, when would this be a nonlinear curve, right? If it was a parabola, if this was some constant plus x squared, right, it'd be a parabolic curve, and it would be nonlinear in nature. Right, but just due to the nature of scattering, it's going to be nonlinear. And so what you wind up with in the end is two knobs. They can turn back and forth, get those best fits, and once you have all that data, fit that against your observed data, minimize your error, and what you have in the end is a very good estimate of your altitudes. So not necessarily a calibration technique. It is, because by the time you tune your atmosphere, what you're getting out of Modtran is now the right parameters for Cal, LU, and LD, again, for all the terms that you need to know. But the extra side benefit that comes out is altitude. Right, so there's a bunch of papers in the literature that of techniques like this that people have used and have got other auxiliary data. There's hundreds of papers out there about water vapor extraction from this sorts of data. This particular scene, this is an average scene, it's a 224 band sensor. Using the technique, the first technique that we did around the water absorption line, what you have right here is a map of water absorption. Or water, I'm sorry, not water absorption, water column density. All right, so what do you have here? Well, you have a very vegetated area and going into an urban area over here. Not a lot of water over the urban area, a lot of water over the vegetated area. Sort of a very nice byproduct if you're into making these kind of maps.
So when you look at the vegetation to account for the aerosols,
Yep.
you look also at the water absorption line?
You're doing both at the same time, right? So you're running Modtran by changing the visibility and changing water vapor. So you're looking at the 760 oxygen absorption line. You're looking at the 940 water vapor absorption line. You're looking at the ratios in there. You're using the same sort of technique in both areas at the same time, but you're adjusting two parameters at the same time, right? So it's a very big computational job to do that. But eventually you'll find the two settings that give you that minimum error term. Right? Typically what you do is you just run a whole bunch of permutations, plot a two-dimensional surface, and use a simplex kind of minimization scheme to find the minimum in that surface, and that's at that location where you plot water vapor versus visibility, let's say, or aerosol concentration. The minimum in that two-dimensional surface would be your solution. All right. That make sense? Okay, let me just do one little quick concept here, and then we'll take a break. Once you do this, once you run Modtran and you get transmission, you get path radiance, and you get downwell radiance as a function of wavelength, and you actually apply it to a particular pixel in the scene, and you invert or get out reflectance, right? So solve the big equation for R, put in all the terms that you know, the observed radiance, the parameters that you derive from Modtran for transmission, and all the other things that are in the big equation. You know all those now. Solve for reflectance. You're going to get a reflectance curve out that so let's say we're looking at that's weird. All right, let's say we're looking at vegetation. Right, it's going to be green. And it's going to go up, and it's going to trail off like this. Right, that's a nice vegetation curve. But what you're going to get out of a reflectance inversion, right, solving the big equation for R and deriving this curve, is you're going to get a curve that looks like this in general shape, but is much noisier. Right, so you can imagine you might get a curve that looks something like this. Same basic shape, but noise. You know that the physics, if you study the physics of scattering and reflection and all the optics that hopefully should be studying, you would get out, you would see the physics, and you would see that these things can't have these sharp lines, these sharp features in them, right? The physics just doesn't allow for that. So you know what you have here are residual effects from materials that can exhibit that sort of spectra, which are gases. Right? Gases can have very sharp spectral absorption lines. Solids can't. Okay? So you know what you have here is some residual atmospheric effect they haven't accounted for. Okay? So how do you smooth it? Well, you take the Fourier transform, get rid of some of the high frequencies, and you back transform, and you get a smooth curve. Right? That'll work. And that's the way a lot of folks would go and attack this problem, and it's not a bad way to do it. It'll give you a fairly good answer. Right? One of the techniques that you can use, though, which is a little more physically rigorous, is something that the industry is called spectral smoothing or polishing, is another term that they call it. I think in ENVI there's actually a pull down for spectral polishing if you go in and look at it. What does that mean? Well, it means you're just going to take all the rough edges off and polish them away. All right, well, it's a really simple concept to do this spectral polishing, but it does require you to know some ground truth. All right, so if there is an object in your scene whose spectral reflectance curve you know, right? Let's say there was a particular patch of grass that you had measured during the overflow, and you went and you looked at that same patch of grass, and the smooth curve under here is what you measured on the ground, and the curve with all the wiggles on it, that's the one you got after you inverted reflectance from your observed radiance data. You know those two should be the same. Right? So what you can do is you can go ahead and you can compute from R, let's see, so make sure the terms are right here. R is the initial reflectance retrieved. All right, so R is what we retrieve. R hat here is going to be the spectrally polished signature, right? The one that's been smoothed. How are we going to do that? Well, we're going to do it really simply with a correction factor. That's a function of wavelength, right? So I here indicates the band from the sensor. And for each band, you're going to have a correction factor to the wavelength. All right, well, how did I do that? Well, imagine, let's just turn this equation around a little bit. If I know a real R on the ground, and I know R that I inverted, well, if I take the ratio of those two, if they perfectly match, the ratio at all wavelengths should be 1. Right? If one of them is high or one of them is low, the ratio is going to go, wiggle around 1. So what I should have here is a series of correction factors as a function of wavelength that really just are probably very close to 1. But they'll have the same sort of structure that we saw on top of our curve. So if I know that, and how do I know that? Well, our truth down here, that's our ground truth spectral measurement that we knew. R is what we measured or inverted from the sensor. Compute that ratio for every wavelength and apply that correction curve to our data and to remove all the wiggles. Right? So a really simple sort of concept, but it does require you to know something on the ground. Right? It does require you to know an object that's in your scene. So either through a spectral measurement, or you went onto Google and typed reflectance curve for concrete, and you got one that you believe. Not as reliable as that. So having something in your scene is definitely the right way to go. All right, make sense? All right, let's take a little break, and then come back and we'll take a look at an example of how you do this in thermal. Or the use of thermal hyperspectral data to drive emissivity. I mean, we talked about driving reflectance by correcting the atmosphere, but the thermal is a little trickier. And this is probably one of my favorite topics. It's where I spent a good almost 10 years of my career with that little blue box on my back, traveling all over the world. So it was a lot of fun. but it's some really cool science goes on in that little blue box. This is a Fourier transform infrared spectrometer. Right there. right? It's a really kind of a neat design. It's a company called D&P Instruments made this, and it's very slick in the sense that there's a computer built into it. This is full Windows-based computer. Little keyboard so you can interact with it. You can see this thing outside. It's awesome. It's not color or anything like that, but you can see it really easily. There's a liquid nitrogen dewar that's right here. Inside is a mercury cadmium telluride detector. This is just a 4-optic on here. So if you look in the little hole there, you can come up if you want to take a closer look. But that's a germanium lens that goes into the dewar, and then right behind that lens is the infrared detector. Right, so it's just a single detector inside of there. And with the 4-optic on there, it's only a little, it's a little mirror inside. Right? So you can point it in any direction that you wanted to. A little sighting scope, so you can look through it and see what you're looking at. And that's it. It's really simple, right? And you gather radiance inside, falls on the detector, and then you have to move the mirrors, right? So just like we talked about the other day with the Michelson interferometer, it's a little bit different of a design. There's actually 2 potassium bromide prisms in here that sit on one another. I'll probably draw a picture here, probably easier.
Could you reduce the stroke?
What's that?
Could you reduce the stroke so the lines are not so big?
Sure. Yeah, this doesn't help. I'm drawing again. So imagine this is a potassium bromide prism, and this is another potassium bromide prism, right? Sitting right next to it. So 2 triangular prisms sitting on top of one another. If I pass the light into this prism and then out the other side, I can actually change the path length by doing the following. Rather than moving a mirror, I can actually take this one prism and slide it along this surface, keeping them in contact with each other, and I could actually change the path length through the prism by doing that. And as a result, I have a fairly vibration insensitive interferometer. Right? I literally, this thing sits on a tripod, I walk around with it, carry it over a shoulder, plop it down, make a measurement, without it really even waiting. So Peter Dibwad and Wynne Wadsworth, who founded this company, came up with that prism design, which was just really quite brilliant. So I can look at a target and measure it. Right? I could turn my 4-optic up, and that's a black body, right? I'll pass this around in a sec so you can take a look at it. But it's, remember the other day we talked about if you took a surface and you put V's in it, all the photons get trapped. Well, that's what they did in here, so you can take a look. But the nice part is they design it, right? So it goes right on the 4-optic, right? And now all I'm seeing is my black body. So I can drive this black body hot, I can drive it cold, I can surround the temperature of the target that I'm looking at, and I can calibrate right in the field. Right? And you can have a little place for it to sit while you're not using it. Right? So here, go ahead and take a look at that. Now, so I can measure two known targets, 2 known black body targets, and I know what the radiance looks like. So I can calibrate what I'm going to look at as far as the target goes. Right? So say I look at the table, I point down, and I can measure what the table looks like, and get it in absolute radiance. Well, that's great. So now I know the target leaving radiance, and it's calibrated. But I still have a problem, right? If my target's not a black body, I'm going to reflect the downwelling radiance, right? So I can make one more measurement, and that's off of this. That's a plate of gold. Isn't that cool? So the first one I ever had of this, I was at Aberdeen Proving Grounds down in. I was somewhere. I think it was Aberdeen Proving Grounds down in Maryland. And I was measuring a bunch of T-72 tanks, right? They wanted to know the surface characteristics of those T-72 tanks. So So I hop up on the tank and I'm carrying my spectrometer and I'm hoping I don't drop it. And I get up there and everything's great. And the whole thing's covered with diesel fuel everywhere too, right? So it's getting kind of grungy, kind of slippery. So I go ahead and I put down my gold plate and I start making my measurements. When you know, along comes this guy, what are you doing? Hops up on the tank, steps right on my gold plate with diesel all over his boots. It's like, ah. But that's okay. Nice thing about gold, you just wash it. You get some Dawn dish detergent, wash it off, and it's as good as new. So here, take a look at that. The nice thing about gold is it is almost 98% reflective in the thermal infrared, and flat as can be. Right? So spectrally flat. So it's almost a perfect white reflector in the thermal infrared, which means it has a very low emissivity. All right, so what do I do with that? Well, I make a measurement of that in the same plane as my sample. Right? So what is it doing? No, it's not giving emissivity. It's reflecting all the downwelling radiance up to my sensor.
You characterize the downways.
I measured it. Yeah, I measured it downwelling radiance and removed it. So you can remove it from the equation very easily.
So this just gives you one number, like an integral over the whole hemisphere?
It gives me an integral over the whole hemisphere.
Okay.
Right. Yeah, so what we're measuring here is diffuse hemispheric emissivity.
When you said in the same plane, so you really want the angles to be exactly the same?
Absolutely. Absolutely. So if that target's flat, I want this to be flat. If that target's 45-degree angle, I want it to be at a 45-degree angle because the things I'm going to see have to be the same. Right? All my background targets need to be identical. Okay? And this is, I think I mentioned earlier on, a little jokingly, but actually I'm very pedantic about this when you make these measurements, is I want to make sure I stand in the same place when I'm making this measurement. I have to be at this little keyboard. So I'm very close to the target. If I move significantly, farther away or closer, I'm going to significantly change the fraction of the hemisphere that's sky and the fraction of the hemisphere that's me. Right? If I have somebody working with me, they need to be in the same place, right? Because we're actually fairly significant sources when it comes down to it. All right, so I make 4 measurements every time. I measure a sample, I measure the gold plate, I measure the black body at 2 different temperatures. Right? So I get perfect calibration all the time. I do 2 other measurements though. Well, I said that's a 98% reflective target. That means it's a 2% emissive target, right? So I need to know its temperature, so I could back out the black body contribution of that plate from the downwelling radiance. And while I'm at it, if I can, I measure the temperature of the target that I'm looking at. Right. Now, measuring the temperature of anything is very hard. Okay, so I didn't bring it down. I meant to bring down one more thing to show you. Let me pull the picture.
Why do you need to measure the temperature if you already have, you're using a spectrometer, so you have the radiance, you understand the reflectance and the emissivity of the target at this point, right?
No, I'm trying to measure. I know the radiance. I don't know anything about the emissivity of the target. One of the things I'm going to show you now is how to measure the emissivity of the target.
Oh, by using, okay.
By using that data. But so what do I have? I have, let's say I have 100 bands that I want to measure the emissivity in. I can measure the radiance in 100 bands, and I can estimate the emissivity in 100 bands, but I have one unknown more, and that's the temperature of the target. So the radiance is dependent on the emissivity and the temperature. So I have 101 unknowns and 100 observables. So I have a problem that I can't solve unless I do it through some iterative solution, and that's what we're going to do. So let me just show you this one other instrument real quick. Look for one of these in a while. Here. Yeah, there it is. All right, I have 2 of these. That's a terrible picture. All right, I have 2 of these upstairs, so I can show this to you at some other point. But these are infrared thermometers. Okay. Now there's a whole bunch of infrared thermometers. They have the ones you stick in your ear to know if you have a temperature or not. Right. Those are pretty good because your ear is pretty much a black body and they do a good job. But they have if you go over to Sears, they'll sell infrared thermometers, and they're these little, they look like little guns. You point them at something, you click the button, it tells you it's 48.7 degrees Celsius. Well, that's crap, right? Because unless you know the emissivity of that target, you can't convert radiance to temperature. Right? So some of the better ones will have a dial for emissivity, but you don't know the emissivity of the target, typically. So you don't get a good temperature. But these guys are great. These are, I don't know if I have a paper posted. There's a really good paper that describes this concept, but essentially there's a detector, little wand that you have, and inside the little wand there's this little dome. Right? So it sort of looks like this, sort of looks like a little pencil. Right? And on the end of that pencil is a little dome inside of it. And it's made out of polished aluminum. Right? So it's highly reflective. So what you do is you put this down onto the surface, and there's a detector right here. And what happens is the energy from the ground comes up, hits here, goes back down onto the ground, comes up over here, hits the back down the ground, comes over here, back on the ground, bounces all over the place. Infinite number of bounces, and eventually hits the detector. Right? What that does is it forces any object, no matter what its emissivity is, to become a black body. Because if you have infinite numbers of reflections inside that integrating sphere, essentially is what it is, it causes every object to become a black body. So now what you see with this is an emissivity of 1, and you measure the radiance and you can convert it to temperature. These things are miscalibrated to 1/10 of a degree Celsius, and they're wonderful. The only downside of it, and it's great, I can measure that gold plate, put it on there, hit the button, got a temperature. I can take this table, do it, get a temperature. If I'm trying to measure grass, that's a little harder, right? Because it's not a nice flat surface that I can put it down. If I'm trying to measure soil, that's not easy. If I'm trying to measure water, it's certainly not easy, right? So there's a lot of targets it's hard to measure. So you can't always measure the temperature of your target. Right? That's the key here. So we're going to have to estimate that temperature somewhere. All right. So this is one of my favorite papers that I've ever read. All right. So it's by some folks from the University of Hawaii, Keith Horton and Paul Lucy. I've met both of them. I haven't met Jeff Johnson in the past. But you know, it's the infrared measurement of pristine and disturbed soils. 2. Right? I guess there was 1. It wasn't my favorite paper. Number 2 is my favorite. All right, environmental effects and field data reduction. All right, so it sounds like a neat title, but what this paper is really about is how you make good spectral measurements in the field. They go a little bit into talking about instrumentation, and you can see right here they're referring to Designs and Prototypes FTIR, which is this guy right here. Andy Korb, who's actually a good friend of mine, helped design that instrument as part of his PhD dissertation. And Jack Salisbury, who was his advisor, made lots and lots of soil measurements over the years. So they kind of came up with the idea of this particular sensor. If you look at this particular one, it's serial number 19, right? So this is one of, I got this when I first came to, I had serial number 1. When I was working down in DC, I had the first one that ever was built. And this one's number 19. So I always kidded them that I was 10% of their total customer base, right? Because I own 2 of their first 20. I think they're up to about 40 right now, so there's not a lot of these things in the world. That little box is about $85,000, believe it or not. And that's why there's not a lot of them in the world. But the technology inside there is just incredible. I took a trip to Alaska once, and I FedExed this up to Alaska. And when I got there, box looked fine, everything looked good. When I took it apart, it didn't work. Well, it turned out that FedEx, it was a really rigid, fiberglass box. It turned out FedEx dropped my box, and it actually sheared the detector away from the heat sink that's inside of there, so it wasn't cooling the detector any longer. So I had to take the thing apart. I had hundreds of pieces all spread over the back of a Ford Excursion, and I was trying to put this thing together. And all of a sudden, I just couldn't think about what I was doing anymore, and it was really weird. There was kids running around on bicycles. I'm like, why am I kind of like losing my mind? I realized it was 2 in the morning and it was still light out. Because I was in Alaska. It was the first time I'd ever been in that sort of environment. So I went to sleep for a while, and the next day we put it all back together and we got it partially working again, enough to make the measurements we needed to. But it was a very bizarre thing. Anybody ever been to Alaska when it doesn't get dark? It's very strange. All right, so how does this thing all work? All right, well, if I go ahead and I measure the radiance of a target, all right, I'm going to get a curve that looks something like this, right? It almost looks like a black body, right? But it has some wiggles in there. And these wiggles are places where the target that I'm looking at is non-unit emissivity, has an emissivity less than 1. Right? So it's not emitting like a black body. And this isn't a perfectly smooth curve because nowhere does it emit perfectly like a black body. Right? But the general shape is close. This is a measurement of the downwelling gradients off that gold plate. Okay, so you measure the gold plate, and this is what the atmosphere looks like as a function of wavelength. So you're looking here from 7 to 14 microns. All right, so it's calibrated radiance. Now, if you read through the paper, they go through a little bit of background, how you do radiometric calibration, but it's actually pretty easy. You measure 2 black bodies, 1 and 2, at 2 different temperatures. You record their raw counts. You set that black body to a particular temperature, so you use the Planck equation here to compute radiance, and here to compute radiance for the warm and the cold, black body again, and you wind up with a calibration factor, ratio calibration factor. So it's really easy to go ahead and get calibrated radiance out. Here you go. All right, so they go through and they present their little form of the big equation here, right? Black body times the emissivity times the transmission to the sensor, plus the reflected downwelling times the transmission to the sensor, plus the path radiance. Okay? So as you read papers, you'll see everybody uses different terminology for these things, but it's all the same physics. All right, they went ahead and did just a couple spectral measurements here of different soils. This is sort of interesting. Undisturbed and disturbed soil. Look what happens to the radiance curve. So this top one is disturbed soil, and this bottom one is undisturbed soil. So this soil that's been sitting for a long time, this is soil that's recently been changed in some way. So it turns out that the emissivity of soil increases after you disturb it. Why would that be?
The ground is hot.
It's just emissivity. It's nothing to do with temperature. The actual optical properties change. The soil is made up of
Moisture in the ground or something?
moisture is a little bit of a problem, but even after you dry it, it'll tend to be even higher. But moisture would certainly make it look more like a black body, because water is a black body. It's actually the fine particles, right? Soil is made out of coarse particles and fine particles, and as you get more scattering at the surface, you trap the photons more. As soil hardens over time and the fine particles settle down and you have coarser particles on the surface, you tend to get less trapping of the photons, and the emissivity tends to go down. So this is, I was working a long time on trying to do detection of IEDs, and you know, things have been buried recently, landmines and things like that, and emissivity of the soil was obviously one of the observables you could look at with a sensor like this. All right, so now, how do you compute emissivity? Well, remember, I took 4 measurements, right? 2 were to do calibration, 1 was to characterize the downwelling, and 1 was to measure the radiance leaving the sample. You could take the big equation, and you could reduce it down to this form right here, where the radiance reaching the sensor is the black body temperature times the emissivity times the reflected downwelling. Well, what's gone? The transmission to the atmosphere is gone, and the path radiance is gone. Right? How can I do that? Well, when I'm measuring with this, I'm a meter away from my target. Right? So if you went ahead and you run Montran in the thermal, and you go ahead and you look at what's the transmission, what's the path radiance over a meter in a typical atmosphere, you're going to get 3 or 4 nines for transmission, and path radiance very close to 0. So you're pretty good to ignore those. Right? So they just dropped them out of the equation. So now, if you rearrange the terms in this equation to solve for emissivity, you get this equation over here, equation 9, where you have the measured radiance from your sample minus your downwelling radiance over a black body at the temperature minus the downwelling radiance, and that's your emissivity. Right, well, you measured this, and this. The only thing you don't know is this term right here. So I could make a guess at what the temperature of my target was, compute this, and I would get an emissivity. But I'd probably be wrong. Right? So let's take a look at what happens when you're wrong. All right. Go a little bit further on in this paper, and let's look at this one. This one right here. All right, now, if the temperature of my target, did it give me a temperature? That's probably the middle. All right, so let's say the temperature of the target is close to 23 degrees Celsius. All right, so that's the center curve. Right, that's the emissivity that I would derive using that equation I just showed you. If I use my black body at a temperature 22.6 in this case. All right, if I use the temperature 21 instead of 22.6, so approximately 2 degrees off, what would happen? Well, my emissivity would rise fairly significantly. And if my temperature was too high, 25 degrees rather than 23 degrees, 2 degrees too high, my emissivity would drop significantly. Right? So the overall magnitude of this curve shifts all over the place depending on that. So I know I have to get my temperature and my target right. If I don't get that, I know my emissivity curve is going to be wrong. Because you can see that's almost 7–8% error that you get in a particular wavelength. So you got to get that right. Now, they made a couple other tests here. I said that gold plate was about 98% reflective. They said it's about 96% reflective. And what would happen if you were wrong on that? Well, it turns out that when you compute emissivity, if you got your emissivity wrong by double or half, right? If you look out here, it really had no effect on the computed emissivity at all, right? So the emissivity of my gold plate, because it's only a 2% to a 8% emitter, right? Really didn't matter, right? Because it doesn't act very much like a black body at all. So as long as I was close, I'm going to get a fairly good response. Where does it have an effect? Well, it has an effect over here where the emissivity of the target actually happens to be low. Right? You can see it has a little bit more of an effect in that area. Right? So you want to be as close as possible. All right, now, if I go ahead and, this is probably a good one to look at right here. If you look at this center curve, it's fairly smooth. Right? It has some wiggles in it, but it's fairly smooth. When my temperature is under-predicted, what happens to some of those wiggles? Look at the structure, right? Look at this particular structure right there. It goes from this little blip up to this huge blip up. Right? That's an absorption line in the atmosphere. And some gas has an absorption line right at that particular wavelength. And by getting that temperature wrong, I don't remove the downwelling properly, or in the right magnitude. So I get an exemplification of that absorption line, and it actually shows here that it's in emission. Now, if I go in the other direction, I get my temperature too high, you can see that that feature actually turns around and becomes an absorption feature. Okay? So you can see that the wiggles get very big if I'm either too hot or too cold, but when it's just right, everything looks fairly smooth. And remember, again, natural materials, hard, solid materials, don't have these lines in them. They're always atmosphere. All right, so knowing that, I can go ahead and I can derive the emissivity of the target by doing the following. I could look at these atmospheric absorption lines as a function of guessing what the temperature might be for the target. So if you come down to this plot right here, what they did was they looked over a very narrow wavelength range. This is 8.1 to 8.6 microns, right? So that happens to fall right here, right where all that atmospheric action is going. Right? And a lot of silicon or quartz-based materials have these things called Rastrophin features, which is this doublet, which is this double dip in the spectrum right around this wavelength region. So when you're measuring soils, this wavelength region is a really good one to look at. Doesn't apply for all materials though. All right, so what do we have here? This is emissivity in that wavelength region as a function of temperature. All right, so here the curve on the top is the coolest temperature, The curve on the bottom is the hottest temperature for your target. The curve in the middle, the real smooth one, that's the one where you guess the right temperature. All right? So when you make those atmospheric lines disappear, you know you got the right temperature. All right, so how do you figure that out? Well, you just run this algorithm, that one equation, you run it over and over again. We're putting in different temperatures for that black body. And you look at these curves and you figure out which one's the smoothest. Now, I don't like the method they used here. They actually fit these dotted lines, which are parabolic curves, to the data, and then plotted the residual error between that parabolic curve and the emissivity curve that they had. They plotted that residual error as a function of temperature, and this minimum point here is the right temperature, right? So now you had, let's say you had 100 bands, you had 101 unknowns, 101 unknowns, all the emissivities as a function of wavelength, plus the temperature, and you only had 100 observables, the radiance, at each of those bands. But using this iterative temperature changing methodology, you can come up with the absolute temperature for that target. So now, not only can I get the emissivity, I can actually measure the temperature. So in your research, if you ever come across a situation where you need to measure the temperature of something, and somebody tells you to stick a thermometer in it, put a thermocouple on it, do any of that, none of that's going to work very well. Right? Even that little sensor I just showed you, what's going to happen when I want to measure the hood of a car, the temperature of the hood of a car, and I put that on the surface of the hood of the car? What's going to happen to the temperature of the hood of the car instantly? Let's say it's the middle of the day. It's going to go down because I'm blocking the sun, right? And the hood of the car has very low thermal mass, right? So it's not going to hold its temperature very quickly, and it's going to go down. If I'm on top of a T-72 tank, right, metal's about that thick, that temperature doesn't change very quickly at all. All right? I learned that because I burned both of my knees over the course of a day. It was always about 65 degrees Celsius, which doesn't sound very hot, but I guess when you kneel on it for the course of a day, it kills all 65 Celsius.
Seriously?
Yeah.
That sounds pretty hot to me.
Well, I mean, but it wasn't hot enough that you couldn't kneel on it. And when I did, when I showered that evening, all the skin fell off my knees. It was like, so I got knee pads for the next day. It was a great experience. All right, so.
Why are these emissivity curves going up to 1.2? I thought
Emissivity does go to only 1, right? But those are the wrong emissivities because I got the temperature wrong. If I guess the temperature to be too low, what do I have to do? I have to push the emissivity up to get the right radiance.
Okay.
Right, so yeah, I mean, I could come to unrealistic levels. And that's a very good sign that you have the wrong temperature, because if your emissivity is above 1. Right, but you notice the one that's here, it's all, down around 0.85 or so. You're in a good range. There's another paper out here on the site, which I like also, not as much as that paper. But it's the next one, number 5 here by Bauer. These guys are at the University of Minnesota, or Wisconsin. They wrote this paper in the same year, and it's exactly the same paper. I mean, it's really wild. They derived the same equations. Right? Check it out. There's the emissivity equation again. And, oh, look at that. I mean, it's weird that 2 researchers, one in Wisconsin, one in Hawaii, did the same thing at the same time. And there's their curve to figure out the temperature. But this one, I like their metric better. What they actually do is they compute the mean squared derivative of the curve. And why do I like that better? Well, it's one call in MATLAB, right? It's one line of code. But actually, both of them work fine. You just got to do something of roughness.
Why wouldn't you just find the average of all the curves and then just see what...
Average of curves?
Yeah, so like, I think the other paper showed it better. But like, if you're looking at it, you know which curve is right just by looking at it, right? You want to find a metric, a computer metric to find that.
Right, but you might not guess the temperature range right.
Oh, okay.
Right? So typically, if I'm outside and it's the middle of the day, I'll put my hand on it and I'll say, oh, it's somewhere between this and this. No, nothing saying that temperature is going to be right.
This was just like a really nice clean
Absolutely.
Okay.
Nice for a paper.
Okay.
Yeah, it would have been terrible if this curve stopped right there, right? Because then you wouldn't have a good thing. that's it. So there's nothing in this paper really about soils, at all. But it was a fantastic paper. All right, any questions? And this is available if anybody ever has a need to measure emissivity or something during your research project. You feel free to borrow this thing, and I can show you how to make the measurements with it. We actually have a project coming up. Actually, we'll probably pitch the project to you guys next quarter when we start talking about all our remote sensing projects, where we're going to have to measure a bunch of emissivities to do some surface modeling as part of it. That's the instrument we're going to wind up to use to do that. No questions? All right. So next time we're going to start to talk about some image processing based remote sensing, right? So I think we're pretty much done with the radiometry portion of the course for the quarter. Now we're going to go and look at how you do some processing on multispectral data, and hopefully by the end of the quarter we'll even be processing a little bit of hyperspectral data. And definitely, if you go on and take the next quarter, John Karekis next quarter will take you through hyperspectral processing algorithms for the entire quarter. And so we'll do some simple stuff during this particular quarter. Some stuff that you'll probably see again in DIP next quarter also. So you'll have a leg up on it. It's going to go on next quarter. That's all I got for you.
Carl, look at the NIST website. Or the website for that estrogen stuff. Look at the first sentence of the handheld precision. They're talking about NIST accurate nanotype level numbers.
Yes, they do.
Really?
That's horrible. Gotcha. Oh, here's a better picture of that one. Here's the little blonde that's on the end.
You just make the wand really small to be able to characterize things that aren't like flat.
It's more of a you have to totally seal it, right? I mean, you have to be that sphere has to be in contact with that surface all around the rim, and unless you have that seal, you're going to let energy come in and out, which
There
changes.
isn't like a malleable material that acts like aluminum. Aluminum foil.
Yeah, I used to use aluminum foil instead of that gold plate when I forget it. So yes, it works. Aluminum foil works really well, and it could seal down onto that surface. Sure. But you'd have to renew it every time, right? After you did that. So I think that's the problem with a malleable sort of material. I mean, you might even think there's you do a lot of woodworking, and when you try and match a profile of molding, there's this neat little tool. It's a bunch of little pins that you press on the surface, and all the pins hit the surface, and it forms a perfect outline of the molding itself. You can do something like that on one of these, and then refresh every time. Sort of like those things. You ever see that it's a bunch of nails, and you put your hand up, and you can see a picture. You know, it's the same sort of a concept. You can do that to seal the edge too. But
Way too much effort.
well, and I don't know anybody that makes one. That's really hard. But this is great, though. I got a little paper, and it's not on the site. I'll try and post it. They explain this concept of multiple bounces and unitizing emissivity by referring to Alice in Wonderland looking into the mirror and not. It's really bizarre. I don't know what kind of drugs these people are on when they make this video. but you read it, and all of a sudden you get it. And you're like, wow, maybe I should take this.